after the properties of matter, which we basically talked about the physical properties. Now the next one in the unit is thermal properties of the matter. So basically, how does my matter behaves with respect to heat? This is what is the chapter right now, and in this particular chapter we will be now taking the PYQ related to that. So the very first one, a copper rod of 88 centimeter and an aluminium rod of unknown length have their increase in length independent of increase in temperature. The length of aluminium rod is, actually it's a bit of calculative question, right? So what we know is, as for the thermal properties, whenever the metal is given the heat, then expansion happens, right? The expansion can be 1D, 2D as well as 3D, okay? So you have a rod where the length will change, okay? So change of length, that is delta. So change of length delta L is equal to alpha original length and delta T, change in temperature, okay? That is how it happens. So whatever rod you have, whatever length it has, if this length is changing by delta L, so this change in length, whether plus or minus, will be dependent upon how much temperature is being applied to it, and at the same time it will be dependent upon the coefficient of a linear expansion. That is basically the property of a matter. It means for the same temperature, copper rod will expand differently, aluminum will expand differently, iron will expand differently. So it is the nature of the material as well, and the formula becomes delta L upon L is equal to alpha times delta T, right? This is what is happening to you. Now what is being told over here is, the copper rod has got length 88 centimeter and aluminium rod you don't know. So for copper rod you will be having alpha times Cu, that is the coefficient of copper rod, and you will have alpha times Al, right? Their increase in length is independent of increase in temperature. So whatever delta L is happening, the length has been chosen, or the length of the aluminium rod in such a way out that delta L by L, right? This particular L, if you write it out, right? Delta L, if I try to write it out for copper, you will write delta L of copper is alpha CUE into length of copper rod into delta T, and for aluminium, delta L aluminium is equal to alpha of aluminium into length of aluminium into delta T. And what the question is talking is, these two, the delta L of Cu and delta L of Al are same, okay? It means whatever temperature you apply, the increments are exactly same. So what you can say is, since these two are same, so alpha Cuu times Lcu times delta T must be equal to alpha of Al, L of Al times delta T, okay? Delta T goes away. So you say, what is given to you? Copper rod length is given to you, but aluminium length you are supposed to find it out. So this is what you are supposed to find it out. So length of aluminium rod will be alpha times Cu into length of rod Cu by alpha times Al, okay? It ultimately comes down to this. Now we put the value, okay? So length of Al is alpha CUE, it is over here, 1.7 into 10 raised to minus 5 into length of Cu 88 centimeters 0.88 divide by aluminium 2.2 into 10 raised to minus 5, right? So this comes down to ultimately, 2.2 into 10 raised to minus 5. So it comes down to 1.7 into 0.88 by 2.2, okay? So this is, okay, it's 17 by 22, right? If you say 18 by 22 is how much? 9 by 11, 0.8 something. So 0.8 into 0.88, right? It is somewhere around 113.9. Okay. Now, instead of calculating all this, again I was telling in some previous chapters, you have to be a little bit intelligent. See where what is happening. When you say that the expansion here, this is looking like a tedious calculation, right? And that is what is the intention of the question setter also. They want to actually spend out time from you if you are not making an intelligent decision over here. What is the intelligent decision? You see here, the original length is 88. So this is 88 over here, right? Now, if the materials are same, the lengths cannot be same. If the lengths are same, they cannot be, they will be expanding differently. So you see, this is expanding lesser and this is expanding more. If you see it out, 1.7 and 2.2, right? So the lengths are going to be, how much it is going to be? Here you see, 1.88 is there. What is the answer coming? Almost this 17 by 22 will come. Almost 0.8, right? 0.8 into 88 centimeter is how much? Some 68 or 70, something like that. Yeah, here it is. You can see it out. So this is your approximate answer. This we can actually guess it out also quite easily, because if you see without calculating or without spending much of the time, how? See here the expansion of alpha cu and alpha L, this is expanding more, okay, compared to copper. So to have the the two expansions to be same, if everything is 88 centimeter, then in that particular case that will expand more. So to have the same kind of expansion, the original length should be lesser. So the answer should be less than 88. That is how 113.9 will not come. Now less than 88 is 68 and 6.8, but 6.8 is too below, because there is hardly noticeable difference between the two expansion coefficients. So if we put an intelligent thought without calculating this much, okay, because this is all calculation with respect to point, fraction, then division and then coming back, we can very easily say the answer is going to be 68 centimeter. NEET is all about intelligent calculations, saving the time. It's not about plain blank calculation, okay. So this, probably this question, when I see it out, a NEET standard question should not be too much of calculations, right? If too much of calculations of this grade are there, that clearly says that it is meant for testing your time management, okay. If the time management is not correct, you go by a straightforward way out, solve everything else. This is the data, this is the calculation, this is the equation, solve it, then come back and see it out. Then probably will be taking out 2 or 3 additional questions time as well, because that is how the questions are set also over here. Here we can see it out, one length is 88 and its expansion coefficient is lesser, whereas others expansion coefficient is slightly higher, okay. So to have the same expansion, my length should be slightly lower, okay. So if it is 88, it has to be lesser than that. 68 is 1, 6.8 can never be, 112 there is no chance because it is on the higher side. So only question what we have is 68. So probably if we go by that approach, we might answer it out in 1 or 2 seconds rather than doing this lengthy calculation and coming back to the same answer. This was my approach of telling you out. Of course, any questions we can go by our theory, by our understanding, solve it out and come back to the question, okay. I felt like this particular question is done towards that end. It is basically set because there is hardly any what you mean to say is very complex kind of question or complex kind of equation or complex kind of understanding. But what I see outstanding over here is quite a lot of numericals, numbers which are in fraction, unknown numbers. It requires a lot of multiplication, division. So it's basically meant for killing the time, okay. But when we go through these options, when we go through the subject, maybe we can answer it out in 1 or 2 seconds, okay. So we should keep that into mind. Let's go to the next. A cup of coffee cools from 90 degrees centigrade to 80 degrees centigrade in T minutes, okay. When the room temperature is 20 degrees centigrade, that is the time this is happening. The time taken by the similar cup of coffee to cool from 80 to 60 degree at a room temperature, when the room temperature is 20 degrees centigrade, what will be that? So what is being asked is, you have been given that one particular instance is cooling from this to this at this ambient condition, right? Now, for the same substance for a different temperature range and different ambient conditions, how the whole thing is going to cool down, right? So, it's basically a straightforward question with respect to Newton's law of cooling, right? Newton's law of cooling says what? Newton's law of cooling says dT by dt. dt is change in temperature, cooling from higher to lower, change in temperature, or you can write delta T, right? Delta T by delta small t means rate of cooling, change in temperature with respect to time, is some constant k T1 plus T2 by 2 minus T ambient. This is your Newton's law of cooling, okay. So, let us put it for first condition. So, for condition 1, it is cooling from 90 degree to 80 degree. So, case 1, it is cooling from 90 degree centigrade to 80 degree centigrade when ambient is 20 degree centigrade, okay. Ambient is 20 degree centigrade. So, write it down over here, 90 minus 80 by T time. It has taken how much time? T. So, it is cooling from 90 to 80 in a time T is equal to, we do not know the constant K. So, we keep it as it is, and this will be 90 plus 80 by 2 minus ambient is how much? 20. Okay. So, that will be 10 by T is equal to K, and this is 90 plus 80, 170. 170 is 85 minus 20. So, we say 10 by T is 65 K. This implies K is equal to 10 by 65 times T. Now, keep this value of K with you, okay. So, we go to second case. What is the second case? The time taken by 2. Now, it is supposed to be cooling from 80 to 60 degree. Ambient is still 20 degree only. So, we say 80 minus 60 by T1, we do not know what is the time, right? T1 is equal to K 80 plus 60 by 2 minus 20, same formula, right? So, this is 20 by T1 is K, and this is 70 minus 20, right? So, 20 by T1 is 70 minus 20 is 50 times K. Now, this K we put this value, okay. So, it becomes 20 by T1 is 50 times 10 by 65 T, okay, and hence time taken T1 will be 20 into 65 T by 50 into 10, okay. Let us solve it. 2 5 10 ja 13 T, 2 5 ja 10. So, T1 is coming as 13 by 5 times T. Yep, you have 13 by 5 times T. So, this is the answer for you, right? Let us go to the next. 3 stars A, B, C have surface temperatures TA, TB, TC respectively, okay. Star A appears bluish, star B appears reddish, and star C appears yellowish. Hence, which is the valid combination? Means by seeing the color of the star, you are supposed to tell the temperature order of them, okay. Again, this we can solve it out, but with a general observation also you can say a rod is getting heated. Once it getting heated, you can see first it looks red hot, you say red hot, then it becomes yellow, and later on when it is super hot, it will look blue for you. So, what you see, color difference when you are rising red to blue side, your temperature is rising. That also you can think of as a general observation and answer it out, but scientifically you can say Wien displacement law, Wayne displacement law. What is that? Lambda is k by t. This lambda wavelength is responsible to, it's not k, it's actually called as b by t. Anyway, it's a constant b. So lambda is proportional to 1 by t. Means the higher the lambda, the lower is the temperature. Okay. And now if you know the Vibgyor series, okay, the wavelength is increasing in this manner. Lambda is like this. So red has got the highest wavelength and blue has got the lowest wavelength. Now where are your colors? A is looking blue. So A is looking blue to you. B is reddish, B is red to you, and C is yellow. C is yellow. Right? So now see in this. So A is blue is highest, right? So lambda A is lowest, right? And B is red, so lambda B is highest, right? And lambda C is in between, right or wrong? Because A is blue, so it is somewhere here on the shortest side, and yellow is in between, so yellow is C, so C is in between, and A is blue, B is red, so B is in the farther. So if this is the order of wavelength, temperature is opposite of that, right? So you can say T of A will be greater than T of C, will be greater than T of B. Let's see, do you have this? T of A, yeah, here you have. T of A is greater than T of C is greater than T of B. So correct answer is D. Okay. And this you practically saw also, that's what I told you. You see from red it goes to yellow and then it goes to blue, and that is how the metal is getting superheated, right? So you can say as the temperature is changing to higher side, you are shifting from red to blue side. The same thing which observed by the Wayne displacement law. Okay. Next. Oh, its a repetition looks like an object kept in a large room having air temperature of 25 degree takes 12 minutes to cool from 80 to 70. Same question which is repeating. The time taken to cool for the same object from 70 to 60 would be just like previous. Okay. So we'll solve it quickly. You remember dt by dt is k times T1 plus T2 by 2 minus T ambient. Let's apply this formula. So first time it is cooling from 80 to 70. So 80 minus 70 by 12 minutes is k times 80 plus 70 by 2 minus ambient is 25. Okay. So 10 by 12 is k into 75 minus 25. Okay. This implies 10 by 12 is equal to k into 50. This says k is equal to 10 by 12 into 50 or 1 by 60. Okay. Now you go k as 1 by 60. So second case when it is cooling from 70 to 60. So let's calculate that for second case. dt is how much? 70 to 60. So 70 minus 60 by t is the time we don't know, is equal to k 1 by 60. 70 plus 60 by 2 and ambient is still 25, right? That's it. You can solve. Okay. So it's 10 by t is equal to 1 by 60. 65 minus 25 is 1 by 60. 40 is 10 by t. This implies t is equal to 60 into 10 by 40. Right? 15. Answer is 15 minutes. Yes, you have. Okay. So this is the solution. Next. Oh, a deep rectangular pond of surface area A containing water which has got a density rho and a specific heat capacity S is located in a region where the outside air temperature is a steady value of minus 26 degrees centigrade. The thickness of the frozen ice layer in this pond at a certain instant is x. Okay. Taking the thermal conductivity of ice as K and its specific latent heat of fusion as L, the rate of increase of thickness of the ice layer at this instant would be given by. Nice, good question. Okay. And it requires a lot of understanding. So, let us do for the decoding of the question first. So, this is a pond, big pond. Okay. It is a pond. Pond has got a water and water has got this ice formed. Why this ice is formed? Because you have got an ambient temperature minus 26 degrees centigrade. This is the problem, right? And this is a water, so which is at 0 degrees centigrade. So, ice is forming. And this ice has got a thickness of x, okay, and it has got a thermal conductivity of K, okay. The water has got a latent heat L and a specific heat capacity S. What he is trying to ask you is, the question is trying to ask you is, what will be the rate of formation of ice layer on it, okay. Say it is right now 10 centimeter thick. So, every second, every minute, every hour, how much will be the layer of ice building on it? This is what is to be asked. This is what is being asked in this question. It's a really good question. So, how do we solve it first? Okay. For solving it out, here there are two concepts. Concept is because there is a temperature outside, it is minus 26 and here it is 0. So, temperature is flowing from here to there. Okay, and as the heat is flowing from here to there, so this water will be getting cooler and cooler and accordingly the ice will form. What will be the rate? The rate at which heat is flowing out of this pond into the atmosphere will decide what rate the ice will be forming over here. Now, for ice forming, what is required is latent heat of cooling, right? So, that latent heat of ice is also given to you, right? So, it means now this pond has got an area A, right, and this has got a thickness x. So, it means you have got an area A and thickness x. So, what is the volume of ice? Volume of ice will be A into x, right? This is the volume of ice and how much is the mass of that ice? A into x into rho. So, this will be the mass of ice, right. Now, this mass of ice will be cooling. So, for cooling how much is required? Latent heat will be required. Now, say the rate is dx, the rate is dx, okay. So, in that particular case heat is flowing out of that, then we should apply the formula of thermal conductivity, okay. What is that formula says? Rate of heat flow dq by dt. Rate of heat flow out or in is equal to thermal conductivity K, area of the block A and temperature gradient. So, what is the temperature gradient? Here it is 0, there it is minus 26. You say dt by L. L is the length on which it is there. So, when I write into this, I can say dq by dt is K A and what is the temperature? 0 minus of minus 26 by L is this thick layer of ice, that is x, right. So, this is the heat which is flowing out of the pond, okay. Now, if it is making a ice of thickness dx layer, okay, then what is the volume of the ice? Volume of ice will be area A, thickness dx, right, and density rho, this is the mass. this much mass of ice is water is getting converted into ice. So what is the heat content? L. So this much of heat per second must be flowing out. Right or wrong? If this much of heat is flowing out per second, only then dx amount of ds thickness of ice will form over here. So now our question is solved. This is the heat which is flowing out and this should be the flow rate of the heat. So this two has to be equal, right? We will write it down now. It will become A dx rho L by dt. This is the actual dq by dt which is flowing out, which as per the thermal conductivity law should be Ka into 26 by x. Right or wrong? Okay. So now you solve it. Right. So if you see over here, A is cancelled. And what you are interested in? The rate at which ice is being formed. So you are interested in dx by dt. Dx by dt is equal to K into 26 by x into rho into L. So we can say dx by dt is 26K divided by rho x L. Let's see whether we have this answer. Yep, 26K by rho x L. Okay, super question. Done. Next, the power radiated by a black body is P and it radiates maximum energy at wavelength lambda 0. Okay. If the temperature of the black body is now changed so that it radiates maximum energy at wavelength 3 by 4 of lambda 0, okay, the power radiated by it becomes Np, N times P. The value of N is. Good question. So what is trying to say is you have a body, black body, right? When we say black body means there is no emission efficiency we are supposed to consider. If it is any other body, the entire power will not be radiated. That is the meaning of black body. So when you say black body, you can say entire power is radiated only, not a problem. So it has got certain temperature. Because of certain temperature, it is radiating a power P0. Okay. Now what has happened is the temperature has changed. The temperature has changed in such a way out, the wavelength is now 3 by 4 of lambda 0. Okay. So in one case, when the wavelength was lambda 0, it was radiating P0, and when the wavelength is 3 by 4 lambda 0, it is radiating N times P0. This is what is this question telling, and then it is asking you what is this N. That is what we are supposed to find it out. Okay. Means what fraction of wavelength, what fraction of power is now being radiated when it has changed. Okay. So this question is also quite nice and it is actually testing up, it's actually towards the black body radiation concept. So black body radiation, you have got two equations if you remember it out, or two laws. One is Wien displacement law, right, no, which says lambda is 1 by T. Okay. Proportional, or you can say B by T, some constant. So you can say lambda is proportional to 1 by T, or you can say lambda 1 by lambda 2 is 1 by T1 by 1 by T2. This implies lambda 1 by lambda 2 is T2 by T1, right? That you can say. Okay, this is what your Wien displacement law is talking. Now coming back to, you have lambda 1 by lambda 2 is T2 by T1. This is what you got. Okay. This is condition 1, this is condition 2. And second is Stephen's law, if you remember, right. This is the Stephen's law which is guiding you, or which is controlling, or which is giving you the equation for black body radiation. What is that Stephen's law? Power radiated P is proportional to, you can write all that equation over here, sigma E T raised to 4. If you exactly want to write it down, you can say power radiated is sigma E A T raised to 4. This is what is the exact equation of Stephen's law. Emissivity, I told you in general for black body and all this and that. So this entire thing becomes constant as far as a body is concerned. The moment you choose a body, this entire thing becomes constant. So you can say P is proportional to T raised to 4. Okay. So here you can say P1 by P2 is T1 by T2 raised to 4. Right? As per the Stephen's law. Correct, no? Now T1 by T2 you can put from here. Right or wrong? So we can say P1 by P2 is equal to lambda 2 by lambda 1 raised to 4 from this. Right? Now a problem is solved. So P1 is given to you as P0 and P2 is given to you as n times P0. Right? This is what the problem is talking. Right? Is P and this is n times P. Here. Power becomes n times P. So you see, one case when the case 1 you have got the P power radiated, another case you have become n times P power radiated. When the P power is being radiated, you have got a wavelength lambda 0. When n times P power radiated, then your wavelength is 3 by 4 of lambda 0. Right? So you write over here is equal to lambda 2 is 3 by 4 times lambda 0 by lambda 1 is lambda 0 the whole raised to 4. So here it goes 1 by n is equal to 3 by 4 lambda 0 by lambda 0 raised to 4, and this gives you 1 by n is 3 by 4 raised to 4. This implies n is equal to 4 by 3 raised to 4, and this will be 256 divided by 81. So your answer should be n should be 256 by 81. Let's see. Yeah, you have. Okay. So that's it. This is how you solve the question, right? You are utilizing the two basic equations, two fundamental equations of black body radiation. One is the Wien's displacement, another is Stephen's law. Wien displacement says you how the temperature varies with respect to the wavelength of the radiation, and the Stephen's law tells you how much power will come as per the temperature coming out of that. Okay. So these are the two fundamental laws. Okay. Next. Fine. Okay. So this much was there as far as the thermal properties of matter is concerned, right, with respect to the previous year's papers. If you see this paper, what do you find? You are being asked here for three things. One is normal, that calorimetry laws with respect to the that is mCV dt or ms into delta T, that is how the heat transfer flows from one body to another. Heat transfer flows to a particular mass for a given temperature. That's one law. Second is thermal conductivity. This is what you saw. And third is black body radiation. So these are the three important sections for this thermal properties of the matter. First one is related to calorimetry and the heat transfer to a body. Second is heat flow, that is thermal conduction. And third is the black body radiation, which is Wien's displacement as well as the Stephen's law. Okay. So these are the important portions in your thermal properties of the matter. So this is we draw the physical properties of matter with respect to solids, physical properties of matter with respect to liquids and gases, which is nothing but fluids, and then we learned the thermal properties of the matter. Okay.